So, welcome back to our Word Logic Day. So, the next speaker is Professor Osvaldo, who is professor at Universidade de São Paulo. Thank you for accepting our invitation, Professor. You're welcome here. So, go ahead.
Well, thank you. I'm going to talk about how to build a causally possible world, but I'm not a logician, so I'm going to try to explain how I came to this topic and explore some connections with metaphysics of possible worlds. And so let me start just making an overview for everyone. So there is an area in analytical philosophy and philosophical logic known as metaphysics of possible worlds, in which the guiding concept is of logical possibility. So a possible world is considered anything that is not contradictory. So, for example, a world in which donkeys speak Tagalog, which is the language of the Philippines. Or as long as there's no contradiction in a donkey speaking a human language, then it is considered a possible world, a logically possible world. A world in which gravity obeys an exponential law, for example. This is an idea suggested by Bradwardine in the Middle Ages. Another example, a world in which there are intelligent dinosaurs. So I'm going to argue that this kind of possibility is not so far-fetched as the other ones. A world in which bacteria are discovered before the invention of microscopes. This is an issue related to science. A world in which Noam Chomsky did not become a linguist. Is this a possible world? Well, sure, Noam Chomsky could have just become a political scientist. This is quite probable, yeah. So these are different degrees of possibilities, right? And we'll explore these differences. Okay, but so why are logically possible worlds so popular in philosophy? So there are different answers. One of them is because it furnishes in semantics an interesting solution for the problem of how to define a property extensionally, which is part of the project of nominalism and its debate with the realism of universals. So for nominalism, it would be interesting if we could define concepts based on sets of individuals in our universe, in a way that being human could be defined as the set of all human beings, which we can extensionally stipulate. So that would be an interesting project. But the one problem is that if we define featherless biped and consider the set of featherless bipeds in our universe, it might be that this set is the same as the set of human beings. So then the project of defining this concept extensionally would not work. So because of this problem, David Lewis came with a solution. If we consider possible worlds, logically possible worlds, then we can imagine a possible world in which we have featherless ostriches. So that would be a featherless biped, right? Or a biped hippopotamuses. So these are featherless bipeds that are not humans, right? So there are possible worlds in which this happens. There are possible worlds in which men have feathers in their ankles. In this world, a human being is not a featherless biped. So by enlarging our world to include these logically possible worlds, we can now define extensionally these two concepts, right? And the sets of individuals belonging to these different sets will be different, right? And that is considered an interesting solution to this problem, right? Okay, so this is just an example of how logically possible worlds are used and have good use in philosophy. But these logical worlds, possible worlds, are kind of far away from our world. I mean, wouldn't it be interesting if we had a criteria to establish what is a more, something that is really possible, not a far-fetched possibility, but a real possibility, right? Which would be consistent with the causal laws of our world, etc. So that's the issue I'm going to consider here. This interest that I have arose when I was working with causal models in the history of science. So this is a project of describing science in terms of certain units of knowledge, certain contributions, which can be ideas, instruments, etc. And these advances are connected by causal relations. So in this diagram, this is a specific episode in physics. But what's interesting is that this particular discovery here of the principle of spectral reversal was arrived at by many different paths. So this diagram attempts to describe the different paths that were taken in this simultaneous discovery. And we notice that we have conjunctions here. So this effect could only arise when these two causes are simultaneously present. And we have disjunctions, which mean that you can have a causal path either this way or this other way is also a possibility. And in fact, in our world, both of them happened, right? So there were two different paths in this case for arriving at this issue here. And there were two different possible paths to arrive here, and then finally, et cetera, et cetera. And so this is like an attempt to describe history of science in terms of causes. And historians are divided. I mean, some of them consider that, okay, we can do that, but others don't like this project of, reducing everything to cause and effect. There's also general conditions that we consider as causes, but there are criticisms to this. So anyway, there are issues involved here. There are discussions involved in this project of constructing causal models. But when we talk about a cause, implicitly, what we're saying is that if the cause did not occur, then a different possible situation would occur as an effect, right? So what I'm saying is that implicitly in any causal stipulation, there is a counterfactual, an implicit counterfactual assertion. So this is the basic intuition for connecting these causal models to counterfactual scenarios, right? Historians are even more, they're not, sympathetic to this view, but there has been some historians that have worked with counterfactual histories of science. Okay, so as I mentioned already, we have these contributions or advances, which are the units of scientific knowledge. So they're an extension of the idea of an idea. to include instruments, data, anything that the scientist proposes, publishes, tells his peers. These are these advances, tacit knowledge, et cetera, et cetera. So these are the units that are causally related, right? And these causal relations, they are of a specific kind. They're probabilistic, right? Let me just give an example of a causal proposition here. Without the Bunsen burner, William Swan would not have proved that the bright yellow D lines arise from sodium. So what I'm saying is that if that instrument were not present at that time, Swan would not have discovered that the yellow light, when we throw salt in a flame, we see this yellow light, but the fact that this is sodium was not so obvious at first, and because the flames were very polluted, etc., and they needed a very clear and pure burner to be able to discover this. So what I'm saying here is that if the Bunsen burner were not there, Swan would not have made this discovery in 1856. Maybe he would have made a discovery later on. Maybe another type of burner would be developed, right? So then you have all these different possibilities that have to be considered when you go deeper into a case study. Okay, so first thing, a few things to be mentioned. We're talking about causal relations, not logical relations. Sometimes a certain episode in science follows a deductive path, but sometimes it follows the inverse direction. We can call it abductive, right? So there's really not a strong relation between logical order and causal order. They're more or less independent, although there are relations. But we have characterized the cause, defined cause in a counterfactual manner. Okay, we can see. I said without the Bunsen burners, one would not have discovered A2. So that's a counterfactual statement, right? So I'm already making use of this close connection between causation and counterfactuals. There is a discussion in philosophy whether you can define every causal relation in a counterfactual way or not. But this is, I mean, there might be exceptions, but in most, at least in our studies, we will do this. We will link both. As I mentioned, cause is something that has many causes, many effects. So this is characterized by the so-called INUS condition. And basically, the way we characterize a cause, we evaluate that a cause changes the probability that an effect may appear in a certain interval of time, delta t. So that's how causes are defined. I mean, if anything changes the probability of an effect appearing in a certain time, then we consider it a cause. So let me give you an example between, I mean, here we have two advances. Just to simplify, we just consider two. A1 is Newton's experiments with prisms and the sunlight. A2 is the discovery that in a solar spectrum, you have dark lines. As we know nowadays, these dark lines arise because the sun its atmosphere has a bunch of elements, and these elements in the solar atmosphere absorb light that is emitted by the sun. And so the spectrum that we receive here has these dark lines, which are not so easy to detect. So it took a couple of 130 years or so for this discovery to have happened. So we have a difference in time here. And in this graph below, I have made an average between these two discoveries. Wollaston and Fraunhofer discovered this independently. So more or less the date of this discovery is around 1808 or something like that. And the idea now is that obviously the time between A1 and A2 could have varied. It's very probable, very possible that, you know, it would take a couple of more years, or maybe the discovery would happen a little bit before. So in our approach, we model this by this kind of a function, which is a gamma function, which represents the distribution of possible worlds related to this very simple question: how long would it take between discovery of A1 and A2, right? And the idea now, I mean, what we did, we use computers, right, to help us work with these models. And we applied this type of analysis for all the advances of a certain episode. So we've had 30 advances that characterize a certain discovery. We apply these considerations. And what we have as a result, we can simulate a bunch of different possible histories in which the times between the events change a little bit. And in the end, accumulating these things, we can have histories in which, you know, a certain discovery that was important for another one, the order in which they appear is inverted. So with this, these possibilities that are generated with the computers, then the historian and the philosopher can analyze and imagine counterfactual scenarios motivated by these differences. So that's our project, okay, in the history and philosophy of science. And so I'm going to focus now on the counterfactual history of the science that arise from these models, but I won't be concerned about the details of the simulations or anything. Let's take like this last example. If Einstein had become a violinist, the theory of general relativity would probably have taken half a century to arise. And relational mechanics, the Machian approach with velocity-dependent potentials, would probably have superseded Newtonian mechanics. So this is an assertion made by a counterfactual analysis of the history of science. What I'm saying is that I consider that this phrase, this proposition, is not far-fetched or random. There are good reasons to support this claim. Although, of course, we have no ways of verifying it, right? So these are not verifiable assertions. But if we understand science, if we understand how science develops, then we will be able to consider whether a certain assertion is plausible or not. Okay, so I will return to this example in a minute. But let me just now answer the question, which is the title of our presentation: how to build such a causally possible world. Okay, so the basic idea is that our intuition is that what we are going to consider as a possible world are the future possibilities that we have right now, for example. So right now, I have future possibilities for tonight. I might go to the movies, I might stay in bed, I might jog or something like that. So these are different possibilities that I know that, you know, I could possibly do if I decided, and these are possibilities, right? So this is the sense of possibility, the only sense of possibility that I will be considering, right? Now, of course, these temporal possibilities that I exemplified in the present time, I can also apply them at a past time. So these past times, we can call them branching times. So I can consider a branching time 100 years ago, and then I can consider the counterfactual histories of our world from this branching time 100 years ago. But this is nothing more than considering the temporal possibilities that were the case 100 years ago, okay? So this is the sense of counterfactual, causally possible worlds that I'm working with. We will see that it will be interesting although I'm not assuming a deterministic world when I say that the future is open, right? I'm assuming this future is open, but in terms of analysis, it is interesting for us to consider deterministic evolutions in a certain period of time, and then at a certain moment of time that we stipulate, I consider a moment of random variation of this universe. So I will say that there's a seismic demon, which every so often gets our universe and creates, say, 99 slightly different copies of the universe. How does he do that? Well, he like shakes the universe slightly so that small random effects make these different universes slightly different. So that will be interesting for analysis, because now I can understand the different evolutions of these different universes, even if they evolve deterministically, since the initial conditions are different, then there will be no problem. And then I won't have the problems of having to explain how identical universe can evolve in different directions. So that's our strategy. And one thing that will appear immediately is that there's a dispersion, which is how strong I shake this universe, which is a variable that you can vary. That you can have worlds that are close, possible worlds that are close, or possible worlds that are more different. And the question of whether what is this dispersion that characterizes our world? I mean, that's an open question. I don't know how to deal with that problem. Okay, so this is right now what I'm presenting to you is an example, a famous example of a counterfactual scenario, which satisfies this causally possible world. So it's the speculation that if the meteor that fell at Chicxulub 65 million years ago had not impacted on the Earth, then dinosaurs would end up being presently, possibly nowadays, the intelligent beings that would dominate the Earth. So we would have reptiles or dinosaurs or something that evolved from them that would become the smartest species and would start transforming the Earth in the way that human beings are doing right now and destroying the world, right? So that would be done by dinosaurs and not by monkeys. So this is quite intuitive, right? Of course, the meteor could have not fallen on Earth, right? So what happened? Well, the meteor came from the outskirts of our solar system, and there was a situation of, extreme sensibility to initial conditions. So the point is, if we consider branching times that are much farther away, like 100 million years ago, and we consider possible worlds that branched here, this is a time when initial uncertainties, the sensibility to initial conditions happening in the outskirts of our solar system, could make the meteor not impact on Earth, but fly close by or farther away, or impact on another planet. So there are many possible worlds here that would not involve this asterisk, which represents this meteor impacting on the Earth. But if we get a branching time that is very close to the time when the meteor did fall on Earth, then the fact that the seismic demon shakes the universe a little bit, would not be enough to make the meteor change its path, because it was already flying towards the Earth. And so for branching times very close to the impact time, most of these worlds would still have the meteor impact. So the probability of having intelligent dinosaurs for branching times T2 is much smaller than for branching times T1, right? So this slide is only to clarify this issue, which is basic and quite simple, but okay. Just interesting comments. So Dale Russell was a paleontologist who seriously considered, this possibility. Although he was criticized for having, come up with a hypothetical view of how this dinosauroid would look like. He's quite similar to a human being, but he considered that this was plausible. And although he was criticized a lot, his answer, he would comment, he would say, look, but when I'm at night looking at the stars, it seems so obvious that the meteor there was a great possibility that it would not hit the Earth. And in that case, it's so obvious that, monkeys would not be the most intelligent beings on Earth, it would be dinosaurs, right? So this intuition, right, is something that guides the construction of counterfactual scenarios, right? Our brains are very good at imagining counterfactual scenarios. And of course, the reason for that is because by evolution, animals that have a capacity for predicting the future, for predicting temporal possibilities, have a selective advantage. So our brains they evolved to a great measure to maximize our capability of imagining future possibilities, and this is equivalent to imagining counterfactual scenarios. And of course, there are other consequences of this. Guilt, for example, is a feeling that arises because of this ability that we have of imagining counterfactual scenarios. Okay. We can do other kinds of analysis. This is another example. Could Brazil have become a communist country? Well, again, if we consider branching times in 1920, the probability would be reasonable. I don't know, 2% or something like that. How do we calculate 2%? Well, we imagine in 1920 making 99 copies of the Earth, shaking them with a certain dispersion, and then of these 100 worlds, 2 of them would have a scenario in which Brazil became communist. So that's what we mean by 2%. Now, of course, if we consider 1970, the year 1970, then the probability of Brazil becoming a communist country was practically zero, right? So again, the branching time is important for establishing these probabilities. Now, this scenario, situation here is like a problem. What's the problem? The problem is, would it be possible for an event, D? What's D? D is Brazil becomes communist at a certain time here. Our factual world is branch 16. So branch 16 is the actual world, okay? And branch 24 here, okay? This is what really happened, okay? Now, we imagined that in 1950, there was a very slight possibility of Brazil becoming communist. And we draw this possible history here, okay? And the question is, could it be possible that this event, or this possible world, could it have arisen from another path 15, which arose when we shook the world here in 1920, and one of these paths could eventually with further jolting here in 1950, end up in exactly the same world as this other path? So this is a question, if this is possible. It is kind of strange, because if this were possible, then in D, people would not be able to distinguish path 15 from path 16. They would not be able to distinguish these two past histories, which is kind of strange, because we have the idea that we identify very perfectly our past histories. So that, and also there are other problems with this possibility. We can have a slight change here, but this will lead to big changes up here in the future. So it would be like a big coincidence that this big change would eventually be parallel to this other big change. I mean, they would have to be very close together here, and that's not very probable. Anyway, so, but these are like issues that can be explored using this model of causal possibilities, in which we have these branching times. And so that's some metaphysical problems. Going back to the history of science, let me just illustrate a little bit better the situation of Einstein. So we imagine that in 1890, the seismic demon shakes the universe and makes 99 copies, or in this case makes 5 copies. So we have 6 parallel universes here. And in most of them, Einstein ended up becoming a physicist, ended up doing the things he did, and ended up discovering general relativity in 1916, or around that era, around that time. But let's consider one possible world in red, in which Einstein has a violin on his table. This little shaking makes the violin fall on the floor. And then Einstein gets very emotional about his broken violin and ends up becoming a musician. So in this world, Einstein did not become a physicist, he became a musician. So what would have happened? What would have happened in this possible world? Well, how do we know? Well, we can ask astrophysicists or whatever. John Wheeler claimed that if Einstein were not there, he thinks that general relativity would only have arisen in 1960. So if a physicist has an intuition of that sort, we take it seriously, right? So, so what we can say is that in this red world here, down here, I'm representing different theories, right? So here we have Newtonian gravitation, which is this main. Here is a transition to general relativity, but here is a transition to the Machian theories, the relational mechanics. In Brazil, we have André Assis, who rediscovered this approach. And it turns out that this approach is better than Newtonian mechanics, because it considers potentials which are more general, because Newton does not consider forces that depend on velocity, or potentials that depend on velocity, but in this framework, this is done. So that allows a more predictive power, more explanatory power. And so this approach is able to explain, like, the advance of Mercury's perihelion and other things. So it is most surely stronger than Newtonian mechanics, but it is not considered to be as strong as general relativity. So in this scenario, this red world, we would imagine that Newtonian gravitation around the 1930s would be replaced by these Machian theories. And these Machian new theories would be able to explain new phenomena, and they would have, they would reign for 30 to 50 years before finally being superseded by general relativity. So this is an example of how, with our intuitions, we can give interesting counterfactual scenarios And we see that by giving this analysis, we understand better the relation between scientific theories, right? I mean, so this is not something that is mere speculation, anything goes. It's not so loose as might be the case in social history. Maybe in social history, these speculations don't have so much restrictions as in history of science, because in history of science, the restrictions are given by nature, right? Nature has a real objective properties, and science is trying to discover these, right? Unveil these properties that the world has independent of human beings. So of course, I'm adopting a realist view here. Just to explain why counterfactual reasoning in science is interesting, while in social history it is not so interesting. Okay, so let's go on and see. This is just another example of how this can be used to clarify our notions. So this is, let's consider this rectangle here. And we have, this represents a possible world, or actual world with branches here. So I should have drawn, many parallel worlds here, but just to simplify, I just drew a simple tree. And so both of these scenarios, I mean, those are these interpretations, imagine that this is possible, that science might be following a certain path. And in a moment of crisis, in a moment of possible paradigm shift, there's a possibility of a new theory branching out and superseding the previous theory. So this is the Kuhnian view. He considers that there is progress in a branch. So like this is, say, quantum theory branching out from the crisis in 1900s. So surely old quantum theory, for example, is stronger than the previous theories. So there is progress. But in the structure of scientific revolutions, he imagines the possibility that at this moment of crisis, science could take another path, another kind of variation of quantum theory could have developed, for example, Bohmian mechanics, something like that, or whatever. And then after that happened, we would still have progress in relation to the past theories. But once science follows a path, it would never approach the other paths. So these would be different possible histories that diverge, right? So what I'm doing here is I'm using this formalism or this approach of drawing trees of possible histories to clarify what is Kuhn's view about science, right? He's not so explicit about all this, but this is what we infer from his views. Now, the more traditional views, the more realist view, objectivist views, like Popper's or the logical empiricist, imagine that this could happen. Sorry. We could have this different possibilities could take place at a certain moment, but in the long run, science would converge to a certain theory, right? So that's the objectivist view of science. So they agree on this possibility here, but they have a different view of how science develops in the future. So this is an example of how to use these diagrams to clarify issues in the history and philosophy of science. Okay, so let me just finish considering some further metaphysical considerations. My time is almost up. So trans-world individuals, well, yes. When I think about my future, whether I'm going to tonight go out for a beer or play soccer, these different scenarios, these different possible temporal possible worlds involve the same individual, myself, right? So it is very natural to suppose that between these different possible worlds, we have the same individual. Well, in terms of metaphysics, how do what's my opinion about whether these possible worlds exist or not? Well, I would simply say that they could have existed. Do counterfactual worlds exist? Well, we know that Lewis answers yes, they are concrete but not actual. Plantinga and others have other solutions, other answers to this. But I think the more reasonable answer is that counterfactual worlds could have existed. And that's all we can say about this. We can't really analyze philosophically this issue further than just using the formula given by our language to answer this. Now, considering the truth value of counterfactual conditionals, my time is up, so let me just rapidly wrap up here. My approach is not to attribute a truth value based on closest possible worlds, as Lewis does. It seems much more reasonable to attribute a probabilistic measure, right? So if I want to consider like a phrase such as, if Chomsky had not become a linguist, then generative grammar would have developed only after 1970. So this is a proposition, and I would like to know whether it's true or false. So the methods developed by Lewis and other metaphysicians try to give criteria to answer our intuitive feeling about this. I mean, maybe we don't have a very good intuition here, but I think linguists would probably agree that yes, this would be the case. But for all I need, I don't really need to claim that this proposition is true or false. I don't worry about criteria pertaining to closeness of possible worlds. It's much simpler to consider just that I can attribute a probability measure for this phrase. So maybe it's 80% true or something like that. So of course I would have to imagine possible worlds from a branching time, which I would have to like 1928, and that's after Chomsky was born. And then I would consider in how many of these worlds Chomsky did not become a linguist, and then I would have to analyze in this set how many of them we would have generative grammar developing after 1970. So this ratio would give me a measure of this truth value, right? And another idea which I've talked with some of you before is the idea that we also have we could talk about impossible worlds, and then attribute negative probabilities to these. So the more negative the probability, the more impossible the world is. But I'm not going to enter this now. Well, this is an analysis of types of possibilities. That's just logical possibility, physical possibility. Then we have physical possibility in our universe, which conserve the constants and the initial conditions of our universe. And then we have causal possibility, which is a subclass of this physical possibility. And an example of something that is physically possible in our universe, but that is not causally possible. Well, one that came up in the history of science is the one I've mentioned before: worlds in which bacteria are discovered before the construction of optical microscopes. So, of course, bacteria can be discovered by other means, by, I don't know, electron microscopes or something like that. But at least in branching times, in 1,000, 2,000, 3,000 years ago, all the possible worlds, of course, will arrive at optical microscopes in a much easier manner. So in all of these worlds, bacteria were only discovered after optical microscopes were developed. So worlds in which bacteria are discovered before the construction of optical microscopes would probably not happen, whatever the time in the past that I return to, because glass is something simple to build, right? Because we have silicon on Earth, on beaches and everything, and so glass is something that's easy. So of course that in all the possible worlds, glass technology will be developed very early in human technology, and microscopes would come at a certain time before bacteria were discovered, because they're discovered by optical microscope. Now we could make another assertion like, oh, if there were no silicon on Earth, then could bacteria be discovered by intelligent beings without the use of microscopes? Well, then yes, this seems to be a reasonable assertion, because there's no silicon, so there's no possibility of constructing microscopes, optical microscopes, and eventually a civilization would discover bacteria by other means. But this scenario cannot be obtained by the strategy we adopted here. There's no point in the past in which we can go and then consider branching universes that have no silicon, because silicon was generated very early on, and even if we consider worlds before that moment, silicon would end up being synthesized because of the laws of physics. So here we have, if this is a physically possible scenario, does not violate the laws of physics, but it is not a causally possible world in the sense that we talked about. The seismic demon cannot make this situation arise. We would need a more powerful demon, a genie in a bottle, something like that, that can create a universe in which there's no silicon on Earth or something like that. Okay, so that's a little bit of the metaphysical discussion again. And just to finish, well, after I worked on these issues, I discovered that Storrs McCall, a metaphysician, a logician, worked out a similar definition of what I call causally possible worlds. He calls really possible worlds, based on this branching. So he criticizes the vagueness of the measure of closeness used by other closeness between possible worlds. He criticized that in Lewis, etc. He, of course, arrives at the idea that you can have transworld individuals. But one thing that he tries to implement is, he's looking for, in the structure that he presents, he wants to give criterias for attributing truth values for counterfactual assertions and not probabilities, right? So instead of closeness to possible worlds, he stipulates that the branching has to be close enough to a certain moment. So anyway, so of course, what I intend to do now is study a little bit more in depth McCall's work. He also has applications in physics, so it's a very interesting author to study, and eventually arrive at conclusions about his view in relation to the one I presented here. So thank you. That's it.
Thank you, Osvaldo. So we don't have much time for questions, but maybe yes, Irina, please go on.
Osvaldo, thank you so much for your presentation. It's very, very interesting. I have a little bit pedantic maybe question. Have you thought about practical applications of this research so far? Could we really create a new science, or could it improve our methodologies or our teaching or learning?
Yes, I think in the history of science, this is a fruitful approach. The only problem is that it's not so easy to construct these causal models. Maybe with artificial intelligence, et cetera, this can be done in a more efficient way. But let me just comment on another issue, which is the application of these ideas to mathematics. So it is possible that, when we consider the history of mathematics, there could be variations in this history. But of course, there are certain events that, certain advances that one presupposes another, right? Like calculus presupposes algebra or something like that, right? And so it's an interesting project to analyze the historical evolution of mathematics and imagine the variations that would be possible. And of course, I think that, of course, this is based on history of science, but in the end, since we are dealing with mathematics and how one theory engenders another, this could, in the end, be a mathematical theory. You could have a mathematical theory of how the history of mathematics develops and could develop, right? So this is, I think, an interesting idea that I haven't seen anyone pursue.
More questions? I have one question. So I was trying to think of counterpossibles on the history of science. I couldn't do, but it surprised me that at some point you mentioned that we can have negative probabilities for impossible worlds. But then I was thinking, first, is this somehow useful for the history of science? Of course, I know it's important for the counterfactual analysis, but maybe, I couldn't see an example of a counterpossible in the history of science. But however, a more intriguing question for me is that since you are open to the idea that impossibility comes in degrees, you mentioned that you can have something that is less impossible or more impossible. And then it seems that you need other logics to enclose the impossible worlds. If you assume, as David Lewis, that a possible word is closed under classical logic, and an impossible word includes a contradiction, then all impossible words makes everything true. So it would be, all of them will be trivial words. So you need, like, for many different kind of impossible words, you need many different kind of logics to run, So this is just to understand how close you come for my own view on this. Thank you for this great talk.
Well, of course, I'm not talking about impossible, logically impossible worlds, but I'm talking about causally impossible worlds, right? I gave an example of Brazil becoming communist would be impossible in 1970, but in 1920, that would be a possibility. The idea of negative measures for probability was explored by Richard Feynman, for example, and some others. And the idea, of course, is that in certain calculations, you can have negative probabilities, but that would not be like a final result. It would be only an intermediary step. In quantum mechanics, you have Wigner distributions, which can have negative values, and that would be an indication of non-locality or something like that. But the idea is that I can have a certain world, and I can vary this world according to a parameter. And it might be that a certain value of this parameter, another situation becomes impossible. And if this parameter is increased, then the degree of impossibility of that situation would also increase. So that's the idea of what this measure, negative probability, would describe. It would describe how far away my constructed world is from a world in which that situation is possible. So I think maybe the idea of distance between possible worlds that Lewis develops is relevant here. Could be relevant. But of course, as I said, I would not apply these ideas to logically impossible worlds, because they seem the measure of, well, we'd have to think about how to measure maybe logically impossible worlds could have a measure of negative probability, but then it would all depend on how they are constructed, what parameter we varied to arrive at that situation. I think it is an interesting question. I'm not just sure how to answer it. But in no moment here I'm thinking about non-classical logics, because I'm not a logician, so I usually don't explore these domains. For me, everything is the logic that I use is our intuitive logic.
Okay. So, Irina, if it's a quick question, maybe.
I have just I have a follow up to Guilherme's question. Maybe if he doesn't know, there is even an empirical research demonstrating that in biological sciences, for example, control possible is a normal practice, especially concerning modeling. For example, modeling some logistic of population spreading or increasing dynamics. So some systems of equations, they are just impossible in integers, to be solved in integers, which is not applicable to population of individuals in the nature. Nevertheless, the scientists do find them reasonable and use a lot. So this is one of the simple examples of contrapositive in science. If it helps.
Okay.
Okay. Thank you.
Thank you, Irina. Very nice.
Well, I'll think about that.
Yes. Well, thank you, Professor Osvaldo, for your talk. And
Thank you.
now we go to Professor Décio. Professor Décio is now teaching at Universidade Federal do Rio de Janeiro, but he worked mostly at Universidade Federal de Santa Catarina. He's a great professor. Thank you very much for accepting our invitation, Professor. So if you want to share your slides, I don't know, maybe you're just going to make use of your voice.
Yes, thank you, Alex. Thank you, Guilherme, for the invitation. It's a pleasure to be here with you. And I will try to pass my slides, but maybe I need your help. Let me see.
Okay.
How can I do it? Are you here? Present now, is it?
Yes, present now.
Present now. Then I enable the whole screen.
Whole screen, yes.
Then, where is it?
You're not going to be able to see us after doing this, but
Where is it? Are you seeing my screen?
yes.
Yeah?
Yeah, I can see.
All of you?
Yes.
Is it okay?
Okay.
Oh, great. Well, thank you again. Thank you, everybody. I will present it now an attempt of solution of a very interesting problem in foundation of mathematics. I call it the Manning's problem. Let me contextualize it first. Let us start with David Hilbert. In 1900, during the Second International Conference of Mathematicians in Paris, Hilbert was invited by Minkowski to present a talk where he offered 23 problems, which was a kind of legacy from the 19th century to the 20th century. It was very interesting because to solve one of the Hilbert's problems was a great step for winning the Fields Medal in mathematics. The sixth problem of Hilbert concerns the axiomatization of the theories of physics. Let's see what Hilbert said. Mathematical treatment of the axioms of physics. The investigations on the foundations of geometry, Hilbert, you know, axiomatized with precise terms Euclidean geometry in 1999. Then this investigation suggests the problem to treat in the same manner by means of axioms those physical sciences which are today, where today mathematics plays an important part. The first rank are the theory of probabilities and mechanics. Of course, quantum mechanics were not known yet. Well, this is the problem, to axiomatize the theories of physics, taking as experience the axiomatizations given in mathematics. But in 1974, the American Mathematical Society sponsored a meeting aiming to reflect about what had been done with respect to Hilbert's 20 problems in mathematics. The interesting thing is that in that conference, a new list of mathematical problems was proposed in several areas of mathematics. And one of them, the first one, was suggested by the Russian mathematician Yuri Manin, a great mathematician, and was a continuation of Hilbert's sixth problem. What he proposed? He proposed to develop a new form of set theory that could cope with quantum physics, where things can be indiscernible, so not forming sets in the standard sense, which, as you know, are collections of distinct objects. Well, this is the first volume of the proceedings of the symposia organized by the American Mathematical Society. Here are the first part of the problems. You can see there the first one dealing with the foundations proposed by Urman. We had 27 problems, if I remember. Well, then he is Yuri Manning. And what he said, he proposed his problem. Let us see an extract of this problem. Item B. Let us read it. We should consider possibilities of developing a totally new language to speak about infinity. You know, the theory of infinity is set theory, developed firstly by Georg Cantor. A new theory, new language to speak about infinity, that is, a new set theory. Classical critics to Cantor, given by Brouwer and other guys, argued that, say, the general choice axiom is an illicit extrapolation of the finite case. This is the criticism to set theory developed by Cantor was that he was not intuitive, used concepts such as the axiom for choice and so on. But Manning sees the problem for another side. Let us see. I would like to point out, said Manning, that this standard set theory is rather an extrapolation of commonplace physics, where we can distinguish things, count them, put them in some order, etc. That is, a classical set is a set of distinct things. You can count them, attribute a cardinal to a set, put them in some order, and so on. Then says Manning, new quantum physics has shown us models of entities with quite different behaviors, even sets, and look for the quotation marks in the word set, of photons in a looking glass box or of electrons in a nickel piece are much less Cantorian than the set of grains of sand. They supposing that the set out of grains of sand can be distinguished, the grains of sand can be distinct of one another, contrary to what happens with photons and electrons and so on. In general, a high probabilistic physical infinity looks considerably more complicated and interesting than the plain infinity of things. That is, this is the Manning problem, to develop a totally different theory to cope with sets in quotation marks, that is, collections of things which can be completely indiscernible, contrary to what happens with sets in the standard set theory. This is the Manning problem. Well, some other researchers said things in similar way. Let me exemplify with the logician and philosopher of science Maria Luisa Dalla Chiara and the physicist and philosopher of science Giuliano Toraldo di Francia. They said the following: consider the electrons of an atom. We generally know perfectly well how many electrons there are, but cannot tell which is which. It is customary to talk of the set, in quotation marks, of the electrons of that atom. But do they really constitute a set? Certainly not in the classical sense. How can we verify that the collections of electrons that are found around the atoms satisfy, say, the Zermelo-Frankel axioms without being able to distinguish one element from another? That is, it's clear that considering such interpretation of quantum things as indiscernible, it challenges strongly the intuitive sense of sets of standard set theories. An example of the absolutely necessity of considering discernible things is given by a very interesting experimental fact called the Hong-O-Mandel effect. But first, look what Frank Wilczek, a Nobel Prize for Physics, said. In the micro world, we need uniformity in the strong kind, complete indistinguishability. Apparently, this is a strong requisite in quantum theory. But let's have a look in the Hong-O-Mandel effect. The thing is that you can here, if you can see my movement, you can send two photons from two inputs here, 2 inputs, and the photons pass here a beam splitter, 50-50 beam splitter, and they go to two outputs. This is the Home effect. What are the possibilities? The possibilities are these ones. We have 4 possibilities. In the first one, from A and B, the first photon reflects in the beam splitter, while the other one, the red one, passes. The second possibility, both of them reflect in the beam splitter. The third one, both of them pass. And the fourth one, the red photon is reflected while the green one passes. Well, the experimental fact is that if you consider indiscernible photons, only the situations 1 and 4 are verified. That is, completely indiscernible photons means the same polarization, sending exactly the same state, with the same energy, frequency, and so on. If even a teeny difference between the photons is detected, then situations 2 and 3 increase their probabilities. But if the photons are completely indiscernible, you verify experimentally only situations 1 and 4. That is, you need completely indiscernible things to explain this experimental phenomenon. Well, indistinguishability is ubiquitous in quantum physics. A long time ago, Erwin Schrödinger said that quantum objects are not individuals, individuals such as we are individuals. The concept of identity, to him, sameness, do not apply to them. And this was reinforced in the 60s by a philosopher of science called Heinz Post. He assumed that this non-individuality, but said more, said that the non-individuality should be attributed to these entities right from the start. What does it mean? It means that we should consider the non-individuality as a primitive notion and not made by hand, supposing that you have individuals, things with identity, and then make some trick in order to pretend that they are non-individuals. This is this standard way we deal with indiscernible things within standard mathematics, set theory, for instance. We use the so-called deformable or not rigid structures, which is a deformable structure. It's a structure, a relational structure here with a domain and relations. And this structure has other automorphisms than the identity function. If only the identity function is the automorphism of the structure, then it's rigid. Let me give an example. The additive group of the integers, the set of the integers with addition. This is a deformable structure. Why? Because the function which attributes to every x its opposite minus x is an automorphism. Then within the structure, inside the structure, you cannot distinguish, for instance, between 2 and minus 2. They are completely indiscernible inside the structure. The same thing happens with the complex numbers, the field of the complex numbers. This structure is also deformable because the function which attributes to a complex number, its complex conjugate, is also an automorphism. So, for instance, you cannot distinguish within the field the complex number I and minus I. They cannot be discerned inside the structure. So we could work within a deformable structure and to pretend that entities which lead one to another by an automorphism act as indiscernible things. But why to pretend that they are individuals? We need to speak in this way because it's a theorem about standard set theory, such, for instance, Zermelo-Franco set theory, that every structure can be expanded to a rigid structure. That is, you can enlarge the structure in order to have just the identity function as an automorphism. Then, even if inside a certain deformable structure, you cannot distinguish between two elements, when you go to the enlarged structure, you distinguish them. And the theorem is interesting. The theorem is that you can ever go outside and you can ever extend the structure to a rigid structure. Furthermore, the whole universe of sets in the standard sense is rigid. That is, one element is indiscernible only from itself. There are no indiscernible things in standard mathematics. I repeat, in standard mathematics, there is no the idea of indiscernible things. You cannot speak about indiscernible things except relative to some few axioms, so few predicates, for instance. But then, if you wish to deal with indiscernibility, supposing a metaphysics of indiscernibility in quantum theory, from the right point of view, you need to change mathematics. You need to change at least set theory. Well, let's see what happens with Zermelo-Fraenkel with atoms. The universe of this theory comprises sets and atoms are elements which can be elements of sets, but are not sets. They are chairs and people and so on. But all entities, sets and atoms, obey the standard theory of identity. This is a theorem which implies that they are distinguishable from themselves. That is, there is no in such a kind of universe with atoms or without atoms, absolutely indistinguishable things. Identity means indistinguishability. So, given two atoms or two sets, they are always different. Given two of them, they are different. What means? This means that the theory presents a property which one of them has the property and another one has not. This is the sense of being different. And in such kind of theory, all entities in the universe of the sets are individuals. The universe of sets and atoms is also rigid. The only automorphism is the identity function. These are theorems. I'm not inventing nothing. This is standard mathematics. Hence, an object is discernible only from itself. Well, how to solve Manning's problem? How to propose a new theory where you can deal with indiscernible things in a complete sense without the trick of making individuals to pretend to be non-individuals. This is the theory of quasi-set. This first version of the theory was proposed in my PhD thesis in 35 years ago, in 1990 at the University of São Paulo. The first paper published was in a journal, in a logical journal, Notre Dame Journal of Formal Logic. And other improvements of the theory done with collaborators along the years have been done until today. This is the theory I will show you, answer Manning's problem. The main ideas. The motivations to construct such a theory follows Erwin Schrödinger's view that the notion of identity does not apply to quantum entities. But there is a primitive relation, weaker relation of indistinguishability, which has the properties of an equivalency relation, but it is not a congruence. To take indistinguishability from the start, as suggested by Heinz Post, the non-individuality of quantum objects is assumed as a primitive notion. The indistinguishability relation does not obey substitutivity, one of the main axioms of identity in first-order logic. That is, from if X belongs to Y and X prime is indiscernible from X, this does not imply that X prime belongs to Y. That is, substitutivity does not hold, hence the indiscernibility relation is not a congruence. Consequently, it is not identity. Okay. How quasi-set theory answers Manning's problem? The theory admits the existence of two kinds of atoms, like Zermelo-Fraenkel with atoms. But here we have two kinds of atoms. The big M atoms play the role of the atoms in Zermelo-Fraenkel with atoms. But the small M atoms are interpreted in ten interpretation as is that they represent quantum objects. And these microatoms are such that the standard theory of identity of classical logic does not hold for them. In what sense? In the sense of the expressions such as X equals to Y are not well formed if either X or Y denotes atoms. The Lange does not speak about their identity. Well, but there is a problem here, because in general, to sets, if you assume the axiom of choice, for instance, you can attribute a cardinal for a set in whatever sense. Then it appears the problem of the quasi-cardinality. A Q set, a quasi-set, may have a quasi-cardinal, And in the finite case, they are not ordinals as in the standard Zermelo-Fraenkel. That is, the usual way to do with cardinals in set theory is to define them by means of ordinals. A cardinal is a kind of ordinal. So we can estimate, using the quasi-cardinals, we can estimate the quantity of elements of a Q set, but this is important, without ordering or count them. This is important because if you attribute a standard cardinal to a set, you are attributing an ordinal, because a cardinal is an ordinal. And in attributing an ordinal, you are ordering the elements of the set. Hence, you are discerning them. You are distinguishing them. Then, quasi-set theory finds a way to attribute a cardinal, a quasi-cardinal, without ordering and without counting. Cardinals in the third item here are not attributed through bijections, projection from an ordinal to the set. So we do not need to discern the elements. And the same, of course, happens in quantum mechanics, for instance, with Bose-Einstein condensates, Bose-Einstein statistics, and so on. This is a typical example. Take the electrons in a sodium atom, 1s2, 2s2, 2p6, 3s1. There is no counting process here. The electrons, for instance, 8 electrons in the second level are attributed by the quantum numbers. You never take one electron and put it there, another electron and put it there, and so on. No. The quantum numbers specify we will have 8 electrons there, but there are no differences between them. The quantum numbers may be different, but you cannot say which electron is which. These are a different sense of distinguishability here. The important thing is that there is no counting process. The attribution cannot be by bijections as standard. What about the mathematics? Then, in order to give rise to such ideas, you need to do mathematics. Then, we have found a way to attribute finite cardinals called quasi-cardinals to quasi-set. We do not require that the elements are discernible. It's not only for finite quasi-sets, because even infinite quasi-sets can be developed in the theory without, and the quasi-cardinal are not attributed by bijections. So we can estimate the number of elements of a Q set without ordering them. They can be difficult to provide all the details. But this is an important point, because there are philosophers who think that we can attribute a cardinal to a collection only if the elements are discernible. They are wrong, because they are reasoning according to standard canons, according to standard mathematics. Okay? The important thing here is that the theory of quasi-set is not a standard theory. Then you can do different things. Intuitively speaking, what's a quasi-set? A quasi-set is something like this thing in red here. You have the case, which means the kinds of things you have, and the lambdas, which are the quantities of them. For instance, take a water molecule here. You can write in quasi-set theory this way. You have H, O, 2, and 1. That is 2 atoms of hydrogen, 1 atom of oxygen. Or a sulfuric acid molecule. You have 2 hydrogen atoms, 1 sulfur atoms, and 4 oxygen atoms. But there are no distinction. You do not distinguish between, for instance, the hydrogen atoms. If this kind of thing was described in standard mathematics, in standard set theory, since we have here 2 hydrogen atoms, necessarily they are different. This is a strong result. Philosophers in general don't take account. Okay, let's go. Hermann Weyl, the great mathematician, tried to work this way, but committed a little fault, a sin. Let me explain. Weil tried to express this idea by considering a set. Look, he took a set with n elements, endowed with an equivalency relation. The pair as the equivalency relation was called by Weil an aggregate. Then, since it is an equivalency relation, you can pass the quotient and take the equivalency classes, Ci. Suppose k of them. Each class has a cardinal, and the sum of the cardinal of the class obviously sum the total cardinal of the set n. This is what Weil called an ordered decomposition. He said, this is what imports for quantum mechanics. You need to know just how many elements you have in a certain class that is in a certain state, but not which elements are there, only the quantities of them. He said, a definite individual state of the aggregate, S, really, the pair, is then given if it is shown for each of the marks N, the N marks P, the classes, to each of the K classes the elements marked P belong. Thus, there are K possible individual states in the aggregate. If, however, no artificial differences between elements are introduced by the labels P, and merely the intrinsic difference of states are made use of, then the aggregate is completely characterized by assigning to each class Ci the number in I of elements of each that belong to Ci. These numbers, the sum of which equals n, describe what may conveniently be called the divisible or effective state of the system S. That is, according to Weil, for physics, for quantum physics, this is what we need. Quantities of things in certain state and not without considering which elements are there. Just the kind of elements. How 5 electrons, 11 protons, and so on. Okay, Weil forgot a detail. The fault came when he considered S as a set, which by the standards is a collection of discernible things, according to our own characterization given by Georg Cantor. That is, Weil intends to consider the equivalency classes as collections of indiscernible things, but they are not. But you can take each class Ci as a quasi-set of indiscernible elements, with the ini expressing their quasi-cardinalities, arriving to what Weil intended to do. You can circumvent the problem Weil found because he used set by using a different set theory. Okay, this theory, quasi-set theory, can be applied to quantum mechanics. The developments are very subtle and mathematical, but here are the main ideas. We can develop a quantum theory within quasi-set theory. My references provided the details. The details and technicalities are many, so we report on the reference. The advantages is that we can consider indistinguishability right from the start, and the standard notion of identity does not apply in all situations. Interpreting as quanta the microatoms may be completely indiscernible without turning to be the same element as implied by classical logic. Furthermore, strong postulates such as the indistinguishability postulate are no more necessary because the language is so that identification by labels is given in principle. That is, you can avoid some strong postulates of quantum mechanics that they are not necessary. The use of the labels 1, 2, etc. are not proper names of individuals, but refer to entities of a kind without individualization. One electron 1, electron 2, electron 3, but without the specification, electron 1 is Cristiano Ronaldo, electron 2 is Brigitte Bardot. No. They are not proper names. They are just a reference given by the difficulties of our language. We need to name them, but then we make tricks, for instance, assuming symmetric and anti-symmetric states in order to mimic indiscernibility. Here, we don't need to do that because things appear directly. Okay, conclusions. Quasi-set theory provides a language for dealing with the collections of indiscernible elements right from the start. The theory and its versions solve Manning's problem, and also Weyl's problem of expressing the effective state of an aggregate out of his mentioned fault. Concerning the foundation of mathematics, it gives a way to question White and Russell's definition of identity, as suggested by Frank Russell in his criticism to the Principia Mathematica. Russell said the definition of Russell and Whitehead definition, which says that things are identical when they are indiscernible, Hansen said, but this is nonsense, because you can imagine the possibilities of things completely indiscernible without turning to be identical. Then he found a fault in Russell and Whitehead definitions. Now we can circumvent that. Okay, these are some works I have participated with Jonas Arenhardt, a professor at the Federal University of Santa Catarina, with Graciela Domenech, a physicist from Buenos Aires, Federico Hollig, physicist from La Plata, Laura Gniksik from Buenos Aires, and me, Graciela again, Stephen French, a British philosopher, and so on. These are few papers. So we have much more. If you are interested, you can write to me. Okay, this is all. Thank you so much.
Okay, thank you, Professor Décio. Great talk. So, is there questions? So I have a question while people
Okay, good.
try to. So one question is, I'm not sure, but as I can see, the quasi-set notion is more closely related with, as you said, atoms, undistinguishable atoms. But I would like to understand how is the relation between quasi-set theory and non-well-founded set theories.
It's different, because a non-well-founded is a completely different thing. Because in a non-well-founded theory, the elements are individuals. They have identity. That's the basic difference.
Yeah, but maybe we have some trouble to distinguish between non-well-founded sets.
No, in what sense?
Individuals
they are individuals. If you give me two elements of a non-well-founded sets, I say to you, they are different. They have a property. Maybe you don't know the property, but it exists. The same thing with the fuzzy sets. The fuzzy sets also, they are individuals too. The problem is that in general, you don't know where they are, but they are individuals. No, it's different, completely different.
Yes. Yeah, I know. I mean, I know it's different, but I was trying just to figure out, because at some point, Peter Axtell and others were trying to develop this idea of graph theory to provide identity criterions for non-well-founded sets, because you cannot count the elements.
This is another mistake from the philosophers. They try to give an example of indiscernible things, graphs. For instance, unlabeled graphs, they say the vertices of the graphs are indiscernible. They are not. What's a graph? A graph is a set. A graph is a set of vertices and a set of edges. It's a set. Then you distinguish it. No, the example is completely wrong. Interesting. A graph is a set.
Yeah, I agree. I agree. I was just trying to hear more from you about this, but I agree.
There is no mathematical theory which starts with indiscernible things from the start.
From the
The
beginning.
only one
yeah.
we know is quasi-set theory.
Mhm.
The other one, you can run about things. You can, for instance, you can do things differently. Oh, I know I can do things differently. I know, but I don't want to do that. Why do not to assume the principle of contradiction for everything? Why not? Because you don't wish to do that. Because you wish to investigate fields where contradictions are possible. Why do not assume the excluded middle for everything? Why? You don't wish to do that because you are intended to investigate, for instance, intuitionistic logic.
Mhm.
Can you make identity, to define identity between the microatoms? Yes, you can. Why don't you do that? Because I don't wish to do that. I would like to investigate a metaphysics. A metaphysics is where things are absolutely indiscernible from the start. This is interesting. This is a huge philosophical discussion, very interesting. There is a result, if I can speak a little bit more. I am working with a mathematician, a Polish mathematician, Elisa Weiss. She's brilliant. She knows set theory, topology, everything you can imagine. And we developed a model of quasi-set theory, where you have quasi-sets with quasi-cardinal 1, where the quasi-set may have even infinitely many elements, if the cardinal is 1. That is, this reverts the idea that the cardinal of a collection explains to you the quantity of elements of the collection. This is now, today, this is wrong. This is an intuitive sense, because you can construct a mathematical where you have collections, quasi-sets in the case, with cardinal 1, but for instance, entangled systems. Entangled system in quantum mechanics, it's a one thing. It must be treated as one system, but composed of several things which cannot be factorized. But it must be treated as one. Maybe it's an example. We are investigating this idea. But it's a guess. It's a completely crazy thing till now.
Good. So Alex raised his hand, but before, I think Gabriel Spaniel was,
Okay.
I don't know, he,
Go ahead.
Hi.
Go ahead.
First, very, very cool, very interesting. But you kind of already answered my question. It was about how we would be able to make a identity relation, not even on quantum, because from what I can understand, it has been separated, the idea of identity and the
Indistinguishability.
yes, in this indistinguishability. And this is very interesting. But then it seems like, is there another way that you can provide a definition for identity, not even only on quantum mechanics or quantum physics, but for a standard object? Seems like our idea of identity is problematic. Yeah, I don't know how we could propose something different, even though the thing we seem to use nowadays seems problematic.
Yeah, Gabriel, interesting question. Because, look, we have an intuitive idea of identity. Philosophers say identity is that thing, a relation, a property, one thing has and share just with itself and with nothing more. This is completely crazy, completely vague. This says nothing. It's redundant. Then you can go to logic. Then you define a logical identity. And there are plenty of logical identities, depending on the logic. Classical logic, modal identity, intentional identity, and so on. Where I spoke there, I refer to the standard theory of identity. This is the identity of classical logic. Is this notion I'm questioning in quantum theory? I not discuss other ways to speak about logic. No, just this one. This notion which is encapsulated in standard set theory, does not work in this interpretation of quantum physics. But if you are a Bohmian, for instance, okay, then everything there has identity. It's a different metaphysics. Then you need to choose the place where you are working. You need I said Voltaire, define your terms. Because you needed to say, identity, I understand this notion. Indistinguishability, I understand this notion. For instance, things can be completely indiscernible and even so be distinct. Can they? Yes, if you assume, for instance, the existence of some substratum, a haecity. But present physics or present metaphysics does not accept that. Classical mathematics has no substratum. Everything is done by properties, is defined by properties. The bundle theories of properties. Okay, then okay, that's all. You can define identity in several different ways, but why? You need to explain. You need to provide at least an informal, intuitive semantics in order to justify what you are doing. In my point of view, you need to justify a metaphysics. Assume a metaphysics of known individuals in quantum physics, and then try to find a corresponding mathematics. Bohmians don't like that. Okay, but they are Bohmians.
Okay, thank you so much.
Thank you, Gabriel.
Alex?
Yes, thanks for the very interesting talk. And I'm coming from mathematics, so indeed, the conception of a set of having distinct elements is completely fundamental, essentially in all mathematical theories. I mean, even the fuzzy sets and all of this. I mean, for me, it's a completely new idea. What you have proposed, and I think. I don't know, I'm not so well versed in foundations of mathematics to really know everything that that's going on, but it really is a completely different, when you talk about foundations of mathematics, some of the most basic ideas are cardinality and ordinals, and one of the most basic ideas that they actually coincide for finite sets. So I think the idea of quasi-sets really is already different at this very basic level, at the very basic idea of identity. So I think it's, for me, it's a very interesting idea, and it takes the time to get your head around, because it kind of, you have to really go back to the beginning, and then you can't fit it into a mathematical series, because all of mathematics essentially you actually start with a set in the Cantorian sense, although actually the whole Cantorian idea of a set is maybe not really historical contingency, but there was a lot of different proposals for what a set should be at the time of Cantor, and at some point they settled on the idea that we have now. I don't even know if at some point the idea of quasi-sets was discussed at that time. I don't know, because historically there were really different proposals of sets. So I'm actually curious if somebody already had some kind of ideas of that. But when I teach mathematics also, the idea of identity and what is equal in mathematics is rather complex. For example, when you teach, I teach a discipline which is called analytic geometry and linear algebra. So on the one side, you have linear algebra, where you have vectors, and vectors are two vectors are the same even if they have different positions, geometric positions. For example, the vector that goes from the origin 0, 0 to 2, 2, you draw it. It's the same vector if you would push it along, and then to the side a bit and say, make it start at 3, 2, and then go 3 to the right, 2 to the right, and 2 up 2. So it's say, if you take the same vector and simply push it to a different place, you would say it is the same vector. But then in analytic geometry, two triangles that could be
Superposed.
they are congruent. Yeah, you wouldn't say that they're equal. Yeah, so this is already something that's difficult for the students because you have different concepts of identity, and then you also have, for example, a simplification of fractions. It's the same fractions. You simplify the same fraction, but if you simplify, for example, say matrices and do Gaussian elimination, yeah? You have a new matrix, but you talk about simplifying the matrix as well, but it's another matrix. Anyway, obviously that are conventions, and it reminds me also of how Henri Poincaré, who said once in an interview that mathematics is the art of calling different things by the same name. So I think the whole concept of identity is actually very central to mathematics, but it somehow I think it merits a more profound treatment. And I think given the needs of quantum mechanics and physical theories, and I think I have to study a bit more. I only learned about this from you, these ideas, and I have to. I pretend to spend some more time on this.
Thank you, Alex.
Very interesting.
Very interesting question. But look, two things, short things. First, if you say the fraction 1/2 is equal to 2/4, you are using the idea of sense and reference from Frege.
Yeah.
You agree?
Yes.
The congruent triangles, the same thing.
Yes.
But classical mathematics, there are, of course, non-Hausdorff topologies. Of course, there are Zariski topology and so on, lots of them. But usually, the space of geometry and so on is Hausdorff. What does it mean? If you take two distinct points, they are different. Different in what sense? They belong to disjoint open sets. Extensionally, a set is a extension property. Then they have different properties. But in quantum physics, maybe things are not so. Because if you have two wave functions, despite the electron, for instance, in the North Pole, in the other one in the South Pole, strictly speaking, the wave functions overlap. Because you cannot ignore the interference terms. They may be a topology, should not have the Hausdorff property, a quantum topology, but it is a guess. Another thing you have mentioned is concerning the vectors. Pay attention, because when you go to linear algebra, you are going to an abstract mathematical structure. Vectors don't have a representation as how can I say, a set, a flash, an arrow.
An arrow, yeah.
This does not exist in linear algebra. This is a geometric idea. What is a vector in geometric sense? It's an equivalence class of equivalent segments. This is the geometric definition of vector. It's an infinite set. Vector is an infinite set of equivalent segments. This is a vector, geometrically speaking. But in linear algebra, there are no arrows.
Yeah.
It's a mathematical abstract structure.
Yeah.
Then it makes the difference. Foundation of mathematics is not a so simple thing. People in general is not prepared to think about the consequences of what they assume. And they assume everything as the engineers do, because everything is disponible. The engineer speaks about infinitesimal elements of volume, areas, and so on. But in this usual calculus, there is no infinitesimal things. We are not in non-standard analysis. In engineering in general doesn't know non-standard analysis. But they use, because it works. Then for all practical purposes, you can suppose that the quanta, one here, another in the moon, are different. You can suppose that. It works. But strictly speaking, it's wrong, because you cannot ignore completely the interference test. I have a quotation here just to finish, given by a great physicist of present days, Maynard Kuhlman, in a book Kuhlman said the following. Pay attention, please, to just this short quotation. A particle inside your body is not strictly inside your body. An observer attempting to measure its position has a small but non-zero probability of detecting it in the most remote places of the universe. This is quantum mechanics. Quantum field theory, better. You do the things in order to simplify things, but look to the foundations, look to the mathematics you are using. It confuses quantum mechanics completely. Okay, but it is I here putting things just for a brainstorming, just for you to think about. I like
Nice.
these kind of things. Osvaldo is quite serious, huh?
So maybe one last question.
Please.
There is one raised hand by João.
Hi,
Hi.
Joe. Can you
Hi.
speak Portuguese? Okay, I can speak Portuguese.
I want to try to speak in English this
Okay.
time because that's some language problem. Esse é um problema de linguagem escutando você. It's right to think identity become a field. When you're saying I'm trying to accommodate the concept of field and set inside my mind. So it's right when you say that the think of identity cardinality, it became a think of cardinality and identity. It became the thought of a field and a set or a set. Tipo, essa conversa toda sobre essas coisas me fez pensar sobre os transinfinitos e sobre os conjuntos e tudo mais. Você tá tentando falar que, tipo, a cardinalidade e a identidade está se tornando um field ou set, um tipo de campo?
Não. Eu não sei o que você quer falar com campo, porque você entra na mecânica quântica, aí campo é uma coisa diferente, né? Completamente diferente.
Isso, eu tô tentando mudar as concepções de campo e de set.
Não. Estou dizendo o seguinte, é que esse resultado que nós obtivemos com a polonesa, não sei, isso é um chute, saiu agora, essa semana. Agora nós temos que explorar isso a pensar a coisa, mas aparentemente a ideia de que o cardinal dá o número de elementos de um conjunto, isso tem que ser repensado. Não é tão intuitivo assim como a gente pensa. Essa é a coisa. Quando você faz matemática formal, você cria monstros. Você cria Frankenstein. Daí você começa a criar lá o boneco lá. E daí você começa a ver o que se fez, o que está acontecendo. Você tem que repensar praticamente tudo. A mecânica quântica, ela revira tudo que você possa imaginar. Ela põe tudo a cabeça para baixo. A noção de intenção, extensão, de identidade, a noção de cardinalidade, ela põe tudo a cabeça para baixo. E isso que é bonito.
Sim, eu tô tentando pensar quais são as consequências práticas em aderir a esse pensamento.
Praticamente nenhuma, porque o físico ele vai continuar. É como eu falei do engenheiro. Acho que o engenheiro vai aprender análise num standard para poder falar em infinitésimo? Vai nada. Ele usa e pronto, funciona. A ponte fica de pé, às vezes fica de pé, às vezes cai. Mas funciona e pronto. O físico é assim. Se ele fosse pensar em fundamentos, ele não fazia física. Não dá?
Entendi.
Isso é filosofia.
Sim. E uma outra pergunta, quando você está falando sobre set em inglês, você está fazendo referência direta à palavra conjunto?
Sim.
Tá.
Set é conjunto.
Tá. Obrigado.
Mas veja bem, João, você tem que, como disse lá, Voltaire dizia, né? Quer falar comigo, defina os seus termos. Você tem que fazer isso. Você vai falar em conjunto, você tem que me dizer de qual a teoria de conjuntos.
Uhum.
Porque pode ser uma classe própria, pode ser um conjunto, como o Guilherme falou, pode ser um conjunto não bem fundado, pode
O
ser
que
um
ficou
conjunto
passando na minha
vago.
cabeça enquanto você estava falando era muito sobre a questão dos transinfinitos. Que eu fiquei, tipo, pensando, nossa, como é que...
A física não usa isso por enquanto, né? As coleções de objetos físicos, aparentemente, são sempre finitas. Eu não sei, talvez algum físico aí possa me corrigir. Mas, então, aparentemente, você precisa de coleções finitas. Quem sabe, no futuro, você vai usar cardinais transfinitos. Mas isso é pura matemática.
Entendi. Obrigado.
Não tem nada.
Ok, muito obrigado. Acho que a gente chegou no
Prazer.
tempo. Todo mundo deve estar doido para almoçar já, então. Muito obrigado, professor Décio.
Eu
Obrigado
agradeço
a
a
todos.
vocês todos, agradeço a quem participou, aos meus colegas, foi bom rever vocês e espero que possamos interagir. Se tiverem algum questionamento, por favor, eu preciso disso, porque eu preciso desse retorno, sabe, assim, questionamentos, mas por que isso é assim, funciona mesmo? Senão porque você não tem sparring. O professor Newton da Costa dizia o seguinte para a gente: se você quer se tornar um bom boxeador, você não pode começar a treinar em casa com a tua mulher e teus filhos. Você tem que ir para o ringue e levar porrada. E eu preciso disso, eu preciso de sparring, eu preciso de gente que conteste, justamente para você colocar, questionar isso. Será que isso está certo? Será que está... É o único jeito.
Muito bem.
Tá, obrigado.
Então, muito obrigado pelo
Obrigado a todos.
sparring.
Tchau, gente.
Valeu, gente. Valeu a todos pelo
Mas
dia.
parabéns aí pela organização do evento.
Obrigado, Décio. Valeu.
Muito obrigado pela presença de todos.
Obrigado,
Muito
a vocês todos. Obrigado. Thank you very much.
Thank you
Bye
very
bye.
much.
Valeu, brigadão.
Obrigado.
Valeu, Osvaldo. Obrigado.
Thank you very much.
Thank you, Irina.